Hi everyone. Today I've got a question for you from the 2019 INMO. So if you want to give it a go, then pause the video here. Okay, let's start by trying to draw a diagram. Now it actually took me quite a few goes to get this diagram to look sort of halfway right, because it's a bit confusing the order that the information is given in. So we have this triangle ABC with angle BAC obtuse. Now D is a point on BC, so let's stick D about there. And E is a point on the line AD. So once you sort of read all of it, you kind of have to read up to here to work out where E is actually going to be. But if we extend this line AD, E is going to be you want to put it so that AE equals CE. So it's going to be about there. And okay, AB is tangent to the circumcircle of triangle ACD. So if we drew, I'm so bad at drawing circles. If we drew a circle through there, then that needs to be tangent to the circle. And we've got BE is perpendicular to AD. So BE, that's supposed to be perpendicular to this line, so that's meant to be a right angle, even though it doesn't look like one. And we have CA equals CD, so that's the same as that. And we want to find angle BCA, so this one here. Now, what I would do first is see what angles I could find that are the same. So we've got all these isosceles triangles, like since we know that's the same as that, then we know that that angle is the same as that one. And we've got that AE equals CE, so this is an isosceles triangle. So that's going to be the same as this one. And then what I would do with the fact that AB is tangent to the circumcircle, I would then apply the theorem that the angle between tangent and chord, so this angle here, that equals the angle in the alternate segment, so it's standing on the same chord. So that's talking about that angle there being the same as that one. Okay, so I'm going to give you two different solutions to this. One is the one that I found, which is with analytic geometry, and it's pretty messy and it has a lot of algebra in it and trig, but it was quite straightforward to do, whereas the other solution that I'm going to show you, the synthetic solution, it's really nice and elegant, but I don't really understand, if I'm honest, how you would actually get the idea to come up with this. That's my problem with classical geometry. Like, there's often these constructions that you have to do where you have to draw in something and make extra points, and like, how do you even know how to do that? Anyway, I'm going to start with that solution, the elegant classical one. So the way that you would do that, by the way, I got this solution off the Art of Problem Solving forums, so I'll put a link to that in the description below. So the solution is, we consider the circle that passes through A, B, and C. So I'll just draw this in here. And then we extend this line AE until it hits the circle. Let's call that F. Apologies for overlapping everything. So that's F. And now let's see what we can do with that. Because I think sort of the motivation for doing this is so that now in this circle we can do like angles standing on the same chord. So I can look at this chord AB and see that this angle here is standing on it, and also this angle here is standing on that chord. So that tells us that that angle is going to be the same as that one. Now let's look at these two triangles here, because we've got this 90 degrees here, so this one's also going to be 90 degrees. And that's going to mean that these two triangles are congruent, because we've got because this is an isosceles triangle now, because we've got that angle is the same as that one. So that tells us that that side's the same as that one. And then we've got, you know, angle, angle, side, angle, angle, side, being the same in those two triangles. So those two are congruent. And that would tell us that the length AE is the same as EF, because they're corresponding sides of congruent triangles. Now, we know that AE equals CE. So now we've got the AE equals CE, and it also equals EF. So these three lengths are the same. Well, that actually means that E is the center of the circle, because it's equidistant from 3 different points on the circle. Okay, what does that tell us? Well, if E is the center, then AF is a diameter of the circle, and that means that any angle standing on it is going to be 90 degrees. So this is 90 degrees here. And then we could look at this triangle. We've got an isosceles right angle triangle here. So each of these angles have to be 45. And that's the same as that, which is what we were trying to find. So the answer is 45 degrees. Okay, so that's a nice, neat solution. Let me show you how I did it. And it's just going to get a little bit messy, but that's all right. All right, I'm going to call this one alpha and this one beta. So we could say, like looking at this triangle, we've got 2 beta plus alpha equals 180 degrees. So we could say that we can solve that for beta. We can say beta is 90 minus alpha on 2. Now, my idea was to sort of use sine rule and things like that in a few of these triangles to try to get an equation that we can solve for alpha. So what I might do is, starting with this one, we've got this nice right angle triangle here. So we could say, like, I might do cos of, that one's alpha as well, because that's the same as that. Cos of alpha is AE over AB. And because, like, my idea is kind of maybe do sine rule in this triangle. So that'll give us a relationship between AB and AC. And then we can sort of look at this triangle and try to get a similar relationship there. Which is why I want this relationship between AE and AB, so that I can sort of maybe eliminate. You'll see. Anyway. Okay, so in this triangle, I want to have like AB, so I'm applying sine rule. AB over sine alpha is AC over sine of whatever this angle is. So let's work out that one. So 180 minus the other two. That plus that. And that's alpha as well. So it's going to be 2 alpha plus beta. So let's simplify that and write that entirely in terms of alpha. So minus 2 alpha and then minus beta, where beta is 90 minus alpha on 2. So minus 90 and plus alpha on 2. So 180 minus 90 is 90, and then we've got negative 2 alpha plus alpha on 2. That makes negative 3 alpha on 2. So here we have sine of 90 minus 3 alpha on 2. Now, in this triangle, what I did instead of using sine rule was, because it's isosceles, I felt it would be easier if we just cut it in half, like this, and then like do sine or cos of that angle. Yeah, probably cos, because so this side here is half of AC. So we could say cos of beta is adjacent over hypotenuse, so the AC on 2 over AE. Okay, now let's see what we can make out of these 3 equations that we've got now. So I might rearrange this to give us a formula for AE that we can sub in. So AE is AB cos alpha. So let's sub that in here. And let's move the 2 down to the bottom as well. So AC over 2AB cos alpha. Now, with the beta, let's replace that with 90 minus alpha on 2. And if we're doing cos of 90 minus something, you can just turn that into sine. So it'll become sine alpha on 2. And then what else do we have? This equation here, maybe we can solve that for AB so that we can sub it in there. So I'm going to move the sine alpha over the other side. So AC sine alpha. And then on the bottom we've got sine of 90 minus something. So we can turn that into cos. Oh, if you don't know what I'm talking about there, with, you know, sine 90 minus being cos, I did make a video on those, so I'll put a link to that up there. Okay, so now we've got that equation and that equation. I might just sub that into there. So 2AC sine alpha on cos 3 alpha on 2 times the cos alpha. And what can we do with that? Okay, let's cancel the ACs. And I'm going to move this up the top. So that's just like multiplying top and bottom of this fraction by cos 3 alpha on 2. That shifts it up the top. So we get cos 3 alpha on 2 on to sine alpha cos alpha. Okay. Now what I might do is shift this over the other side, because I don't like having fractions in equations. If you can get rid of them at all, it makes things much neater. So I'm just multiplying both sides of this equation by 2 sine alpha cos alpha. All right, now we've got these alphas on 2 here, so I think what we want to do is express everything in terms of that. So I might say let theta equal alpha on 2, and then we can rewrite this in terms of theta. So that is 2 theta, and then we've got cos 2 theta and sine theta equals cos 3 theta. Now, I actually don't remember the formulas for triple angles off the top of my head. I actually had to go back and think of it like that, and then use the angle sum formula and yada yada, simplify. But it comes to 4 cos cubed theta minus 3 cos theta. Okay, and then I'm thinking what we want to do is just write everything in terms of cos theta. Let's first expand this. So that's 2 cos theta sine theta. That's just double angle formula. So let's combine the 2 from that with that 2. So we get 4 cos theta sine theta, and then let's combine those 2 sine thetas. So we get sine squared theta. You know what, actually, let's not have sine squared theta. Let's write everything in terms of cos. So that'll become 1 minus cos squared theta. So that's that and that combined, turn into that. And then we've got the cos 2 theta, which is 2 cos squared theta minus 1. You might remember it as cos squared theta minus sine squared theta, and then you can replace the sine squared theta with 1 minus cos squared, and it simplifies to that. Okay, now what I might do is expand these. Not the cos theta though, I'm not going to bring that in because we can take out a factor of cos theta here as well, so maybe we'll be able to like cancel the cos thetas from both sides. But if we expand this, I'm going to do that one times that one first, because that gives us the highest power of cos. We've got cos 4 theta, and then that one times that one is plus 1 cos squared theta, and then we've got that one times that one, which is another 2 cos squared theta. So we're going to end up with 3 cos squared theta, and then we've got minus 1 from those. And let's factorize that. Let's bring a cos theta out the front. So 4 cos squared theta minus 3 cos, no, just minus 3. Okay, now let's consider if we can cancel the cos thetas. You have to be careful. I mean, you probably know this already if you're doing Olympiad level questions, but you need to consider, can cos theta be equal to 0? So what would happen if that's true? Well, theta would have to be like 90 degrees, or, I mean, 270 or something, but it's not going to be 270. So let's think about what happens then. Alpha would be 180. So that's obviously not possible, because that was alpha, is that angle in the triangle. So that's not going to happen. So we can sort of say, like, that's impossible. Like, therefore, cos theta is not equal to 0, which means that we can cancel this off both sides. And let's expand the 4 in there. So we get negative 8 cos to the 4th theta plus 12 cos squared theta minus 4 equals 4 cos squared theta minus 3. Now, when I sort of saw this at first, I thought, quartic, not good. But it's all right, because there's only cos to the 4th and cos squared, which means that we can treat it as a quadratic. Anyway, you'll see that in a second. I'm just going to move like all of this over to the right-hand side. So we'll get 8 cos to the 4th theta. So we're subtracting 12, and that'll combine with that to make minus 8 cos squared theta. And then minus 3 plus 4 is plus 1. Okay, so sometimes if I'm like a bit sleepy and can't do a lot of jumps at once, I'll say, let x equal cos squared theta, and then rewrite the equation in terms of x and do it that way. But if I feel like sort of skipping steps, I'll just go straight to saying what cos squared theta is, because this is like cos squared theta squared, so it's like a quadratic. I'm just going to apply the quadratic formula here. So when I do that, I like to work out the discriminant first. So b squared minus 4ac, so 8 squared minus 4 times 8 times 1. That's going to be 64 minus 32, which is just 32. So we'll have the negative b, so positive 8, plus or minus square root of the discriminant all over 2a, so 2 times that. And then let's simplify this a bit. Let's do like 8 over 16 as a half, and then plus or minus. This, if we think of the 32 as 16 times 2, then you'll have like root 16 times root 2, so 4 root 2. And then 4 root 2 over 16 is root 2 over 4. Okay, that looks really ugly, but it's actually not going to be so bad, because what we want to find is alpha. So let's think about cos alpha is cos 2 theta, which is 2 cos squared theta minus 1. So we can just plug this into the cos squared theta. So 2 times this is 1 plus or minus root 2 on 2, and then we've got the minus 1. So that just makes plus or minus root 2 on 2. And you'll recognize that as the cosine of 45 degrees. So alpha would be 45 degrees. You can ignore the negative solution, because alpha is not going to be obtuse. So we're not expecting things like 135 degrees as solutions, because it said that angle BAC has to be obtuse. So alpha is going to be acute. So probably in the proof, I would do like a little explanation here that alpha's between those. Okay, so that was the way that I did it. It looks really long and messy, but I was able to sort of come up with that idea fairly quickly. I didn't have to do too much trial and error to come up with that, whereas I feel like the classical solution, this thing with the circle and all that jazz, you would have had to do quite a lot of trial and error to think of that. But maybe it's just because I'm more comfortable with analytic geometry. Maybe if I had more experience with this sort of thing, I think you sort of build up a repertoire of, previous solutions to problems that you've seen, and then that gives you ideas for new ones. So maybe if you've seen a lot of Olympiad level geometry questions, you'd be able to easily think of drawing this circle in and extending this line to make this point, and so on. But I'm not really at that level yet that I can come up with solutions like that. Anyway, let me know in the comments if you can explain what your sort of train of thought would be to come up with that solution, or if you had another solution that was nice and elegant that you want to share, then just leave a comment so everyone can see it.